Good morning, students. Am I audible?
Yes, sir. Good morning, sir.
Good
Yes.
morning.
Good morning,
Good
sir.
morning.
And I'm sharing one screen. Is it visible from your side?
Yes, sir.
This white screen, right? Okay, so
Yes.
myself, Dr. Rajiv Kaur, I'll be taking this BJT part. This is actually, I think some of the topics have already been discussed by Professor Mahapatra and Professor Majumdar, right? So diode and PN junction, the physics behind this PN junction, these are already been discussed. So assuming that you know what is the fundamental concept of p-type, n-type, and how to fabricate this junction, and what are the drawbacks and what will be the characteristics of this junction. We'll proceed to this bipolar junction transistor. That will be today's topic, and actually I work on this semiconductor device modeling, right, and circuit optimize, as well as for the signal processing circuit also. Okay, so that is my area of specialization, and for that reason only probably I have been given this topic to discuss in this class, right? So we'll discuss. Is it visible what I am writing on the screen?
Yes,
Yes,
sir.
sir.
Yes,
Yes.
one of you please respond all the time. If because see, I have opened this white screen and I don't know what's going on at the back. This MS team, and I have never taken any class in this MS team, right? So this is the first time I'm dealing with bipolar junction transistor. Okay, and we'll quickly go through this because some of the aspects you have already gone through in your class 2 physics level. Bipolar junction transistor, right? Transistor means transfer of resistor. So somewhere in between there will be a resistance difference in the device. Bipolar junction transistor was developed by a famous scientist, Shockley. He was in Bell Lab in 1951, and actually two more scientists were there, Budin and Bratton. They actually worked under Shockley only. Okay, so he was reporting authority of Barden and Bradley, and in textbook you probably you have seen that there are three scientists who have been awarded Nobel Prize for the discovery of BJT. Okay, so in 1951, actually there are two patents filed on this BJT. One patent was individually filed by Barden and Batten, and the second patent was by Shockley. And the credit goes to all these three scientists. Okay, so that's a short history regarding BJT invention. It has got three terminals whose output current, voltage, and power. This will be controlled by the input current, and that is very important. Input current will control your output current. It will control the output voltage, and which you have not studied probably, the output power also. Okay. So it's the input current which is very, very important to define the characteristics of any BJT. I will use this abbreviation all the time because bipolar junction transistor will take a longer time definitely. So BJT consists of two PN junctions. So far, so you have studied single PN junction. Okay, in conventional PN junction diode, there were only one PN junction. Here, you will find there are two PN junctions. This is one junction, first junction. This is the second junction. Okay, NP or PN, whatever it is. The circuit could be, or the structure could be like this, PNP. Here also there will be one junction, first junction. Okay, there is no first or second junction. I am just marking this. There are two different junctions. Okay, so whenever you will find there are two junctions, in general, it will come under BJT category. Okay, it has got essentially three regions. One is called emitter. Second one is called base. Third one is called collector. Okay. This side is called emitter if I mark it for NPN transistor, this is called NPN transistor, right? This is called PNP transistor, depending on the configuration of the different junctions. Here you will find in PNP, you will find two different P junctions are there. Sorry, two different P regions are there. NPN, there will be two different N regions will be there, and those two N regions will sandwich this P region. Okay. So this emitter region is situated in one side of the transistor. Then comes base, then comes collector, and this is the orientation for any BJT. Okay. Emitters, the terminology emitter means it emits, that means it supplies charge carriers to the other two regions. An important feature of this emitter region is it is heavily doped, or should I say, out of these three, it is the emitter region which is having the highest level of doping. Base region will have least doping. Collector will be having intermediate. Okay. So base will be the middle region, and that forms 2 p-n junction in the semiconductor or transistor as a whole. And the base of the transistor is thin. So these are the properties you can write down. The base of the transistor will be the thinnest, should I say, out of different three regions as compared to emitter, and is lightly doped region. And should I say, it is the least doped region. The collector is situated on the other side. I've already, so this region is collector region. It will be on the other side of this emitter region. Okay, and the collector signifies that it will collect the charge carriers which emitter has supplied. If you look at the area of this collector of this transistor is always larger than the emitter and base of the transistor, so that it can accommodate, it can collect maximum amount of charges which would have transferred from emitter through base to the collector. And the doping level, I have told, the summary is given. Sorry, the summary is given. The doping level will be intermediate for collector region. This first I have written, second I have written, these are called junction. The first junction which I have marked is called emitter base junction, because this junction is between emitter and base. The second is called, either you can say collector to base or base to collector junction. Here also you will find, so this is emitter, this is base, this is collector. Okay. Here also first junction will be marked as emitter to base junction. Second junction is called base to collector or collector to base. Okay. There are different ways you can fabricate this BJT. That is different manufacturing technique. Those who are interested, they can refer to one reference book available on Velasat technologies. Technology means it will give you the physics behind this semiconductor fabrication and all these things, written by SMG. Okay, so actually this book is, whatever I am writing in 4 or 5 sentences, actually the book contains each and every details of this manufacturing technique. Okay, so because it's a very fundamental course for your engineering curriculum. So I'm just giving you the highlights. What are the current technologies available for fabricating BJT? Techniques are grown technique, alloy of fused junction. Third one is diffused junction technique. Fourth one is epitaxial growth. Okay, and there are many more. Okay, all are uh, somewhere down the line are similar to any one of these four techniques. And presently, most of the semiconductor industries follows this epitaxial growth technique. Okay, due to several reasons. Okay, so there are four techniques, at least these four you remember, these are the fundamental techniques. Even if you come across any other technique which is discussed in SMG book, you will find that this comes under, it falls under any one of these four categories. Regarding the symbol of NPN, there will be an arrow which will specify the emitter terminal, right? The other two will be base and collector. This is the symbol for NPN transistor. Okay, if the arrow is towards the device like this, again it will be an emitter terminal. This will be PNP device. Okay, so only arrow will define whether it is NPN or PNP, and depending on that, the voltage that you will apply across different terminals will be different. Will be different in the sense the polarity will be different. Now, you cannot work on, only with this transistor. There has to be certain voltages, those are to be applied across these different terminals, and that will generate some input current. And I have already told input current will determine the performance of the transistor. Whatever might be the application. Mostly in your syllabus, you will find the amplifier is the application, but there are many more applications of transistors. Okay. So you have to finally generate current, and to generate current you have to apply certain amount of voltage different across two terminals. Okay. So whenever it comes the voltage applications, that is called biasing. So either there could be an unbiased Bjt where there is no voltage applied across these three terminals. Okay, the situation is like this. If you have got three region, let us consider with NPN. Remember, PNP discussions will be exactly the same. Only difference will be the polarity of the voltage. Okay, so this terminal will be emitter, this terminal will be collector, and this terminal will be base. Okay, and you know this majority carriers for N-type semiconductor is electron. Okay, so let us consider lot of electrons, abundant electrons are there in N-type. Here also there will be a lot of electrons. Okay, and probably you have come across how the junction is been formed while discussing this PN junction. So there will be a penetration, because here there will be a plus sign, right? And it will enter to this N region and get combined with the electrons and get neutralized. Neutralized means it will be immobile. Immobile means it is not free electron or free holes. Okay, so I am putting a plus sign and then inside a circle. So this indicates these are all immobile carriers that will not take part into conduction. On the other side, let us say this electron probably will be transferred to the P region, and again it recombines with the holes present there, okay, and gets neutralized. So it looks like this. So this plus and minus, this particular region, okay, will never take part into conduction. Similar story will happen here also. There will be plus here, okay. Plus means electrons might have transferred to this P region. So it has left one hole open here, and then it is minus. This region, these two regions are called depletion region. Okay, you can say this region is called collector to base depletion region. This is called emitter to base depletion region. Depletion means, depleted means remove. That means you have removed the charge carriers from this particular region, and it will look like an insulator. Okay, because it is there is no free charge carriers. You can say this is just like an insulator. So there are two insulator region and the region will occur across the junction. Width will be different depending on the voltage or depending on the doping level. The higher the doping will, or should I say, will reduce the depletion region. Higher the doping, depletion region will be reduced. Why? Because if doping is high, then this will try to press this particular immobile positive carriers. Here, if the doping is very, very high, then it will try to press as much as possible towards this junction. So the penetration towards the higher doping region will be very, very less. Okay. Now coming back to this unbiased BJT concept, if the transistor 3 terminals, emitter, base and collector are left open, this is called unbiased. There is no biasing, there is no voltage present across, or should I say voltage applied across emitter, base and collector. And under these conditions, the diffusion of electrons across the junction produces two depletion region. One is emitter to base depletion region, one is collector to base depletion region. And ideally, if there is no voltage present, then the barrier potential of each of these layer at 25 degrees centigrade is approximately, okay. Don't argue that in textbook it is given 0.66 or 0.67. There are many other factors. Should I say almost 100, more than 100 parameters are there which will determine this particular value. And it's a separate research topic, those who are working on the semiconductor devices model. In general, for your course, you understand and you have been studying, it's 0.7, but truly speaking, it's not 0.7. Okay. So 0.7 volt, a rough approximate at 25 degrees centigrade for silicon and 0.3 volt for germanium. That means even if you don't apply any voltage, there will always be this much amount of voltage that are to be overcome by the external voltage. That means if you apply a voltage which is lesser than 0.7 volt for silicon, there will be no current conduction. First you have to overcome this particular barrier. It's just like a wall, right? You have to jump over it. So minimum voltage will be just greater than 0.7 volt. You will find certain amount of current flowing through this semiconductor. Okay. One more aspect is, because these three regions have different doping levels, I have already told emitter is highly doped, or should I say the most heavily doped region. What happened? Sharing is paused. Is it visible? The screen is visible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
What happened? It
Yes,
was
sir.
showing sharing was paused.
No, sir, it is visible.
Okay. See, at the background, don't do any engineering. Huh? Otherwise, no, I'll foolishly keep on talking and then it's saying, oh, where is your shared window? Sharing is paused until you return to the shared window. If you don't see this screen, because I have just opened the screen, so if you can't see it, tell me immediately. Because there are three different regions, right? One is emitter, one is base, one is collector. These three regions having different doping level. And I have already told doping level will determine the amount of depletion region. The higher the doping, lesser the depletion region. So definitely depletion region also do not have the same width. What I am telling, this particular depletion width will definitely
Sir, your
be
voice is breaking.
Is it?
Okay, fine.
Yes, sir.
It is fine, sir.
Sir, fine, sir.
I don't know that.
Sir, it is
At
fine, sir.
least I assure that
Fine.
I don't have any throat problem. That much I can assure. But if technology doesn't support me, I can't help it.
It is
Right?
fine. Sir,
Yeah.
doping of P
There
region
is
will be
fine.
high.
Please, one of you talk at a time. Don't sing in chorus, please. Yes, somebody was asking question. I'll just give 5 to 10 minutes at the end of the lecture. Will it be okay?
Okay.
Because then the flow will be disturbed, right? I think that will be the best practice. Thank you.
Okay.
So what I was telling, this blue covering which I have done, okay, these two regions will definitely have different doping levels. Sorry, different depletion region width. The reason is emitter region is having highly doped compared to the collector region. Okay, and I have told the more heavily doped region has more heavily doped region means greater concentration of ions, right? More number of free carriers are available, and that will try to press this depletion region towards the junction. So the penetration towards it, towards this particular region will be less. And if you observe from this particular conclusion that higher doping reduces the depletion region width, you will find the emitter based depletion layer penetrates slightly into the emitter. The reason is emitter is highly doped region, whereas it penetrates deeply into the base as it is a lightly doped region. So I will just draw this particular region. You will find this side is emitter, this side is base, okay, and if I consider this is the depletion region, this will be the scenario of the depletion width. Okay, so the depletion width, so if I say this is the junction, okay, this is the junction, so the penetration at the emitter will be much lesser compared to the penetration of base. The reason is the doping. And in a similar conclusion you can draw for collector to base region also. Okay, collector to base region, depletion layer penetrates more in the base region. So if I draw the collector region like this, and this side is base region, so this will be the penetration for, and this is the junction. Okay, and out of this emitter to base and collector to base, which one will be having more depletion layer width? Okay, because the emitter base junction, emitter is highly doped. Can I say the emitter base depletion layer, depletion region is less than collector to base depletion region? Why? Depletion region is inversely proportional to the concentration. So definitely the higher the concentration or higher the doping, lesser will be the depletion layer. Okay. So this is the story regarding unbiased BJT. Whenever you do biasing, sorry.
Sir,
Yes.
can you please show the slide before
Slide. This slide or previous one?
Okay, thank you. This slide only.
Oh. See, till this particular point I was discussing regarding a transistor which doesn't have any external voltages which you have applied across the transistor. Now, if you are going to apply a voltage, because finally you have to generate a current for this transistor, right? So that is called transistor biasing. Okay, so the formal definition of transistor biasing is the application of a suitable DC voltage. That's very important. Okay, you have to apply a DC voltage across the transistor terminals is called transistor biasing or biasing. And each junction of this transistor can be either forward biased or reverse biased. And while discussing this junction, you might have come across, whenever it is forward biased, current will be allowed to flow through it. If it is reverse biased, current will be almost negligible, or should I say the amount of current will be zero, ideally. Okay. So depending on that, there are three different ways of biasing. Please switch off your mic, somebody. Please switch off the mic. I can see whose mic is on, right? And it's recorded, remember. I need not to do anything. I've already told this arrow will signify, first you will write down this is emitter terminal. Okay, this is base, then this is collector. Now this arrow will tell you the direction of the current. Right? So if current is coming out of the device, you can say, okay. So if it is coming out of the device, this terminal is negative and this terminal is positive. Here, the total current, because I've already told whatever current you are injecting at emitter terminal, okay, so I write IE, that will be split into two different components. One, a very small portion will.
Sir, can you repeat again?
I'm just starting. Wait. There are two different components by which your current will be getting diverted. Okay, the total amount of current is IE. Okay, one small component or fraction will be diverted through the base terminal. Approximately in textbook it is written 2%, 3%, but I don't give any percentage because it all depends on your design. Okay, nowadays this is almost 0%. Okay, so very if you look at the latest technology, people actually don't go for any base current. And sometimes you will find the base region is so fabricated that that small amount of current which is coming out of this is sufficient to carry out certain functionalities. So if you come across any statement like this, that collector current is the main component which is being used for transistor performance, absolutely wrong. Okay. There are certain devices where base current is the major component. Why? Because those particular systems demands a very less amount of current. Okay, so these are few advanced information compared to your class 2 physics. And the current which will reach to this collector region is called collector current. Okay. So this is called forward bias, means the current will be allowed to flow. If I write this is emitter, this is base and this is collector, current you are injecting at emitter terminal, some component will pass through, right, through the base terminal, and the rest amount of current will be reaching to this collector current. The voltage, the DC voltage which you have connected here, battery should I say, okay. This terminal is negative, this terminal is positive, that you understand. And the nomenclature is given voltage across E and B, right? So BEB. Here this is positive, this is negative, and the voltage is denoted as VCB. That means voltage across collector to base. Okay, you can write VCB, here you can write VBE, but remember, I'll tell you the little difference between VBE and VEB. This indicates VB is greater than VE, right? This indicates the emitter voltage is greater than VB. Okay, so there is a plus minus difference between VEB and VEB. So while using this particular notation, you should be careful which particular terminal is more positive compared to the other. More positive, I have told. I have never told positive. Okay, because you will find both are at negative voltage. You have to find out which one is more positive compared to the other. This is called forward biasing. So current will be allowed. Why? Because emitter, base and collector. This terminal is given as positive voltage. See, this is NPN, right? And you know, for PN junction theory, if this is P, this is N, if this fellow gets positive voltage, then only current conduction will take place. So somehow you have to give P as positive, N as negative, right? Look at this. What is emitter for NPN? This is NPN transistors, right? Base is positive, so I have connected base to the positive and N to the negative. And that's the story for PN junction forward bias. The same concept, only we are dealing with two different junctions.
Sir, in that case, it must be VB, no, sir?
Which one?
Yes.
B is positive, then it must be VB, no, sir?
Yes. Have I written anything else apart from VEB?
Okay,
Sir,
sir. ठीक है, sir.
VB
It should be
See,
VB.
if you
Notation must be
V
V.
is greater than VB.
no.
V is positive.
See, don't make it a
VB
debate
is
class. Listen to me. Listen to me. Whatever knowledge you have, actually you have almost I've seen for my last 20-year careers. Okay, not you are not even born. You people have a half-baked knowledge. See, whenever I would have written VBE, in that case I would have not given minus and plus sign, right? Minus and plus I have given categorically. I have shown that this is upper one is negative, lower one is positive. Okay. For this first time and last time I am writing this plus and minus. Other henceforth you have to understand it, and I will change it accordingly. Okay. You cannot give a negative sign and then you write VBC. If I write like this, what does it mean? So I have written it, right? What is this voltage? Minus VEB voltage, right? You used to write minus 12 volt. You know what is the difference between minus 12 volt and plus 12 volt? There is no difference in minus 12 volt and plus 12 volt except the ordering of the terminals, positive terminal and negative terminal. We don't have any minus 12 volt supply as such. Okay. What I have written in this way, minus BBE, or sorry, minus BEB I have written here. Okay, in this terminal. So both don't give symbol as well as because that's what you are accustomed to. Specifically, I have given to show that this terminal is negative, this terminal is positive, and that is why I have written BEB. Okay, and most cases you should write VBE. Understood?
Yes, sir.
So if you are giving plus and minus, be careful.
Yes, sir.
This is the PN junction concept. Now the second saturation. Saturation means, again I am discussing this NPN transistor, and you know emitter current will be flowing out of this device, and I have told total emitter current will be. So before drawing this bias voltage, I have just marked these different current levels, because this IE will be the final current. Okay, so that will be equal to IC. So here IE is coming out of the device. What I have made IC and IB both going into the device. Now you look at the direction. If it is negative, that means this terminal will be positive, this terminal will be positive. Now come here. You have to generate the current from here, so this will be positive and this will be negative. Right? Is it okay?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
No. See, these two are same. That's what I have drawn it. This and these are same. If you make it forward bias, both here actually, one is forward bias, this particular is reverse bias. So this comes under forward bias conditions. Okay. What do you have to do? You have to change this. I'll tell you why. And then current will not be in this direction. This will be negative, this will be positive. Okay. So this is collector terminal, this is base terminal. Right?
So, but then how current is being generated there?
Listen, wait. Wait. It is not like that you are making one battery and it's generated. Battery never generates a current. How many do know this? How many of you
Sir,
agree
it
that?
only provides the potential difference.
Will only pumps the
Yes, sir.
charge.
Potential difference.
Yes.
Potential
So
dif-
it allows this barrier to be overcome, and it keeps on circulating the charges across the circuit. So don't have this mindset that how the current will be generated by this. Okay? It's not the current generator. Okay? I'll tell you why. I'm just giving you the different configurations of the transistor in different bias arrangement. First one was forward bias. This is saturation, and the third one is cutoff. I'll tell you the different different bias statement also. Cutoff means there will be no current flowing as such. Okay. It's like this. This is this emitter, this collector, this base. Okay, it's VCB or VEB. Now look at this. There will be no current here. Okay. And even if there is no current in IE, there will be no current in collector and there will be no current in base. This particular region or this particular working domain is called cutoff domain or cutoff bias, you can say. You bias in such a way that the current flowing through the transistor is cut off. There are three different bias elements. Now I will give you the different junction status for different conditions. One is, it's called forward. First one is, where is first one? Here. Forward biasing or forward, in some textbook you will find it's written forward active biasing or active biasing. So these are all same nomenclature. I have put it in single statement. One is forward, second one is saturation, third one is cutoff. Okay. Now what are the different junction bias conditions? Okay, you have got two different junction. One is emitter bias, one is collector bias, right? When it is forward bias, now you will find what sort of bias voltage you have to apply, whether positive terminal will be connected or negative terminal will be connected. If it is forward bias, and that is the normal working conditions for any transistor to be used as, remember and listen to it carefully, used as an amplifier. For any other applications, the other biasing elements could be a choice. For this case, the emitter bias will be forward bias, collector base will be reverse bias. If it is forward bias, that means the amount of resistance is less. If it is reverse bias, amount of resistance is more. Okay. And here lies the concept of transfer of resistor. Here the ratio of output resistance and input resistance will almost give you the gain of the transistor, gain of the circuit. Okay. So the larger the difference, more will be the gain you can get out of the circuit. But if the working conditions, somebody raised these questions, how you will generate current. I am least bothered about generating current. Okay. It's not the collector current that we are generating. We are generating only emitter current. Collector current is the received current. You remember in that way. Okay. When both are forward biased, now you understand, if both are forward biased, collector to base, what is collector? Collector is N type, right? And base is P type. What happens when an NP junction is forward biased? And you have to generate these forward bias conditions. Now you compare and see whether NP is really forward biased or not. Forward biased means, right? You apply a positive voltage to P type, negative voltage to N type. Look at this. This is N. It's an NPN transistor. It's an NPN transistor. So this is N. Base is P. N is negative. P is positive. Is it forward biased? So this side is forward biased. Here it is N because it's an NPN transistor. This side is P. N is positive. So this particular region is also forward biased. Okay. So when both the junction are forward biased, the working domain is called saturation. Okay. And when both the junctions are reverse biased, look at this. This is N type, this is P type. This is N type, this is P type. Now if I put a reverse bias, that means P will be facing negative, N will be facing positive. See, for both the cases it is happening like this. N is getting positive here, P is negative. N is getting positive here, P is negative. So here both the junction, first junction and second junction, both are reverse bias. Okay, and that will lead to the cutoff conditions. So cutoff, you will find the first junction is reverse bias, second junction is also reverse bias. Remember, whenever it is forward bias, resistance is less. Whenever it is forward bias, resistance is less. Whenever it is reverse bias, resistance is as good as infinity. Whenever it is reverse bias, resistance will be as good as infinity. Okay. So this is the for NPN transistor, and the biasing or the voltage polarity will be applied according to the working domain that you want. Now it's not that saturation is not used, cutoff is not used, it is only the forward bias which is been used for actual circuit. No. Okay. It all depends on how much resistance you want at the output side. Okay. If you need a smaller resistance at the output side, then you have to go for this. Okay. If you need a larger resistance for both the cases, for the input side and output side, then you have to actually go for the cutoff conditions also. Okay. There is a term called impedance matching. Okay. In earlier, the cable operator used to give one black coaxial cable to your home, and you might have connected to your television set. Okay. There is a small impedance kept on that at the edge of this cable. Okay, at the end you will find there is one impedance small unit is there. Okay, that is around 75 ohm. Okay, now let's say your 75 ohm is coming and this side is, let's say, 750 ohm. Okay, there is a unit called impedance matcher. That means this 750 ohm, see this side is low. You understand? I am telling you where exactly you can apply this. Forget about this amplifier. Amplifier story ends here itself. This side is high. This, which one will you choose for this case?
The first one.
Your circuit is somewhere here. Your circuit is somewhere here. And if it is 750 ohm at the input side, right? And 750 ohm at the output side. You have to match with this. Please switch off the mic. Why you are so stupid? Listen to this carefully. Amidst all these difficulties, your friends are waiting to listen. Only this matching purpose, there is a called matching network also, impedance matching network. Mostly in television set you will find, at least in your home appliances, this has been used. Okay. So what you have to do, you have to match with the 750 and 750. You know this maximum power transfer theorem, right? When the two impedances are same, you can transfer the maximum amount of power. Okay. Here it is not so. Okay. So what you have to do, you have to drop down to some voltage, and which will be matching with this 75 ohm. Okay. So this side will be reverse bias, and the output will be forward biased. So that is also one more configuration. It all depends on which particular application you are going to use. That means your input will be reverse bias, output will be forward biased. Okay. NPN probably will not give you this. For PNP, you will definitely get this sort of applications. For NPN, you will get forward and reverse, forward and forward, reverse and reverse. PNP will be just opposite of this NPN configuration. Okay. So I'll okay. If you have any questions, I'll stop because another 5 minutes are left. The class is up to 10:45, right?
Yes, sir.
Yes.
Yes.
Okay.
Yes.
Any queries, questions, suggestions?
Sir, excuse me,
Sir, will
sir.
you please repeat, sir, R, what is RO by RI? Previous slide, sir.
Yes, sir. Yes, sir. That gain stuff is told about.
Okay, I don't know where I've written. I will tell you. See the transistor
Yes, sir.
term.
Yes, sir.
Yes, I have seen. The transistor is actually transfer of resistor. Okay, in this way only they have derived or coined this nomenclature. Now, whenever you have let's say I apply 5 ampere. Now don't go for this unit. Okay, 5 ampere is too high. Okay, except power transistor, 5 ampere will be very, very high. If it is low, right? So what will be the input voltage? Low means what will be the resistance? Resistance will be low, right? So what will be the input voltage? Let us say input voltage is resistance is 10 ohm. Okay, I am just arbitrarily assuming. Here I have told resistance is high. Output side. Why output? Because I am assuming emitter, I am injecting certain amount of current and the output is collector side. So collector to base will be considered as output. Emitter to base will be considered as input. In circuit I will discuss in details, but preliminary because you raised this question. What will be the input voltage as such? 5 ampere into 10 ohm because what happened? 50, right? This is the input voltage. And resistance here, let's say this is 1K. And I assume same amount of current is passing through this base. There is no base current getting leaked out. So the final current will be reaching as 5 ampere. So what will be the final output voltage? 5 into 1000, right? What is the output voltage now? 5000. What is the gain of this system? How do you define gain? Gain is the final output voltage that you are getting divided by input voltage. So this is 5000 divided by 50. Now you understand how the resistance.
More than 100.
Huh?
Sir,
Yes,
5
sir.
10.
Gain can be more than 100.
Gain can be of any value. It all depends. See, at the beginning, see, you are disrespecting what I have told. I have taken an arbitrary value just to tell you what is the meaning of R0 by Ri.
Okay, sir.
Now don't tell me whether it can sustain 5000 volt or not. Okay, then I could have given 0.1 and then calculation would have taken certain time. You understand the philosophy what I am telling, that you give the same amount of current just due to the difference in the resistance at the input level and output level. Same amount of current. Again, I have told there is an assumption. There is no current getting out of this base current. Okay. So whatever current goes to the output side, that multiplied by the output resistance will give you the output voltage. Okay. Ohm's law. Even though it is not applicable, first of all, because Ohm's law is applicable for linear device. Okay. This transistor and PN junction is purely non-linear device. Again, Ohm's law I have applied, but remember, because you are quite accustomed to that particular law. Although except few conductors, nowhere it is been applied. Okay. So just due to the change in the resistance level, there will be a change in the output voltage, and you get gain out of it due to the variation of the input and output. Yes.
Sir, if we instead use one 10 ohm resistor and 1000 ohm resistor, so what is the difference of that and using this NPN junction?
Well, I am not using any resistor here. I have never used 10 ohm resistor. Oh, you are telling if I use one 10 ohm, no, then?
Yes, so if instead of this diode, I am using 10 ohm resistor and 1000 ohm resistor in series. So
Right.
what will be the difference? I mean, then also I will be gaining this 5000 volt and
Right.
5000 volt output and
You can get.
50 volt.
You can get, but the major advantage of using semiconductor is that the first condition is that it can be used as a automatic switch. Okay. So whenever I need, I can easily just change this voltage polarity and I can make it cut off. But if it is a 10 ohm to 1000 ohm resistor circuit, until unless you switch off the battery, the current will keep on flowing through it.
Okay, sir.
Remember, amplifier, please switch off the mic. Amplifier doesn't mean that it can be only realized with help of transistor. There are many other ways you can realize an amplifier. Transistor is one way to approach this amplifier concept. Please switch off this, it's too irritating. The gentleman who has switched it on. Who is doing this? Who is the seer of this class? Who is the seer? Who has switched it on? Keshav Kumar. Keshav Kumar, I am marking your roll number, right? Why you have made it on? Keshav Kumar. What's your roll number? 10109. Okay. Okay, any other queries?
So have you taken attendance?
It will be automatically counted. MS Team actually takes this. At the end, whenever I will switch it off, it will automatically be counted. Don't worry. Any other queries?
No, sir.
No, sir.
No,
Impedance
sir.
Well, somebody was asking. Yes, yes. Impedance?
purpose of impedance matcher.
Impedance matching network, right? Impedance matching network is when there is a difference in the impedance. Let's say this is 5 ohm and this is 50 ohm, right? And you need a channel to be connected. And there is a theorem probably in your, I don't know whether you have studied in class 2 or it will be in electrical concept. Maximum power transfer theorem. Okay? Maximum power transfer theorem. It says that power will be transferred maximally only when the load impedance is equal to the source impedance. I repeat, power will be transferred at its maximum level when, that means if you have, let's say, here it is source impedance is like this, load impedance is RL, only when RS is equal to RL, and there is a rigorous proof available. Okay. When RS is equal to RL, you can transfer maximum power. Now, if the situation is like this, your input is somewhat 5 ohm, output is 50 ohm. What do you have to do? You cannot do this. Okay. For matching network, you cannot connect, because if you connect a channel like this, definitely power will be transferred, but it will not be at the maximum level. So what they do, they take a network means it's a circuit combination of some active and passive devices, right? Here you will find they connect, let's say 50 ohm, here they connect 5 ohm, so they connect like this. Now what is the actual input impedance, or should I say source impedance? If I put it in series, let's say 55. What is the output source load resistance? It is now 55. Could I make my point clear? So this is your RS source resistance together, 5 plus 50. This is the load resistance, and I have made it RS equal to RL purposefully to follow the maximum power transfer theorem. Now the power will be transferred maximally, and definitely you have to pay cost for this particular circuit. This is called matching network or impedance matching network or impedance matcher, whatever you say. Could I answer?
Can you repeat the statement that power will transfer at its maximum level?
Yes.
Can you repeat the statement, sir? Power will transfer at its maximum level.
Power will be. I'm not getting you properly. Would you please be louder and clear?
So he is asking for the statement maximum power theorem.
Maximum power transfer theorem says that power will be transferred maximally, or whatever good English you can use, Maximum power transfer is possible only when the load resistor equals to the source resistor. That means source impedance should match with the load impedance. Right? Now, you don't argue that, okay, there will be resistor in between this path. Let us assume either that comes under load side or source side. Okay, so I am just taking two major division. One is source resistor and one is load resistor. And don't ask what happens to the in between if there is any resistor comes load and source. Any other queries?
No, sir.
No, sir.
No, sir.
Okay, so next class we'll discuss the operation of NPN transistor and PNP transistor. Mainly, I'll be taking 4 classes at most. Okay, I'll try to complete as much as possible. Okay, thank you very much.
Sir,
Yes.
Thank you,
Yes,
sir.
children.
share this notes.
Hello.
But can you share it?
Huh?
Can you share these notes or PDF?
Whatever I have written, I will just make this PDF and upload. I will ask your Professor A. Mojumdar to help me in this regard. I am very novice in this. Okay, I will do it. But whatever I have told you, don't expect that all I will write on pen and paper and then I will upload. Whatever I have written on this this particular screen, that much I can save it in PDF and then I will upload it. Right?
Yes, sir. With this, we want this only.
If that serves your purpose, hopefully you will get that.
Sir,
Yes.
sir, what is the difference between BJT and transistor?
Transistor is a family, right? BJT is a member of that family.
Okay, sir.
Under transistor, there are different transistors. Does it make any sense?
Transistor.
Right?
Okay.
Like I'm from core family and we have many cores in our family. Does it make more clear? BJT under this, there are different transistor. In your syllabus, you probably will study this BJT. Then you will have field effect transistor. Then you will have metal oxide semiconductor field effect transistor. And there are many more.
MOSFET.
Yeah, MOSFET is metal oxide semiconductor field effect transistor. These three actually, should I say, there are again different versions of MOSFET. One is enhancement type. No,
CMOS, enhancement MOS.
that's I told no. Half-baked food is actually a bit confusing. It won't be digested. Your CMOS doesn't come under this MOSFET category.
No,
MOSFET
sir,
is
it's complementary MOSFET.
See, don't. Whenever I am not asking question, okay, don't show that you know. You probably know this. Okay, but what I told, there are other students also. They want to know. Okay, if some of your friends have raised these questions, let me ask because government knows my potential and that's why they have given my job. Right? Otherwise, you could have made a
Excuse me,
separate.
sir.
Yes.
Sir, the ECC exam, electronics exam.
Regarding exam, you talk to Professor A. Mujumdar, right?
Okay, sir. Thank you,
He
sir.
is the UC coordinator.
Okay, sir. And sorry for the inconvenience created. Sorry, I by mistakenly.
CMOS actually is the combination of different MOSFETs. Okay. MOSFETs also have got two different types. One is enhancement type of MOSFET, one is depletion type of MOSFET. Out of this, depletion type of MOSFET is again obsolete nowadays. It is the only E MOSFET which is currently running the semiconductor industry. Out of EMOS, there are two types of EMOS. One is N type of EMOS, one is P type of MOSFET. P type of EMOS. These two coupled together in a suitable manner leads to CMOS. Okay, somebody asked these questions regarding CMOS and this thing. CMOS does. Yes. Could I answer this point? Somebody was asking field transistor. Okay, I've told you the total
Sir,
at least
sir,
should
can
have
we
to
leave
your.
now?
Yes.
Sir, can we leave now as our next class is from 11 a.m.?
Yes, you are always welcome. If you don't, if you have not, if you have understood, you can leave always. Somebody asked these questions. Could I answer your point?
Yes, sir.
Okay. So I'll leave this meeting because you have got other classes as well. Okay. Thank you very much. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.